Monday, June 2, 2025. Arctic Blue Ocean Event 2025. Update June 2025. High temperatures. The image below shows the temperature anomaly, versus 1951 to 19,801, for May 2025. The large difference in anomalies on and around Antarctica is striking, highlighting the predicament of the West Antarctic ice sheet. How large is the temperature rise now? In the image below, created with NASA data, the decade from 1903 through 1912 is used as a custom base, illustrating that temperature anomalies were 1.5 degrees Celsius or more above this base for the past 2 years, i.e. for each of the 24 consecutive months from June 2023 through May 2025. So, when using 1903 to 1912 as a reference, the temperature rise has clearly breached the 1.5 degrees Celsius threshold for the averaging period going back 2 years through May 2025. What is the best reference period or base against which the rise is to be measured? An earlier analysis suggests that the rise may be even higher when compared to a genuinely pre-industrial base. What averaging period is most appropriate in analyses that include the temperature rise to come? The issue is discussed below. In the above image, the red line, 2-year lowest smoothing trend, shows a steep rise that, when extended, points at 2 degrees Celsius above this base, 1903 to 1911, getting crossed in late 2026, implying both goals of the Paris Agreement have been breached, i.e. to limit the temperature increase to 1.5 degrees Celsius above pre-industrial and to limit it to well below 2 degrees Celsius. What type of trend is most appropriate in analyses that include the temperature rise to come? Using a lowest smoothing trend and extending that trend linearly into the future may not be the most appropriate way to go. The image below shows a polynomial trend, calculated over data from 24 months ago, June 2023, through May 2025, and extended 24 months into the future. It's a cubic trend indicating that the temperature rise may be 3 degrees Celsius in 2026 and 5 degrees Celsius in 2027. A 3 degrees Celsius rise in 2026 and a 5 degrees Celsius rise in 2027? Click on images to enlarge. How bad could 3 degrees Celsius or 5 degrees Celsius be? The image below adds some perspective. It is from the 2019 post When Will We Die? Screenshot from earlier post. Would things look much better when calculating the temperature rise over a longer period? When using only past data, the average anomaly for the period starting 12 months ago through May 2025 is 1.67 degrees Celsius. For the period starting 24 months ago through May 2025 it is 1.69 degrees Celsius. When using an averaging period starting 10 years ago through May 2025, the average rise is 1.41 degrees Celsius. Going back further in time can reduce the average, but such an analysis would incorporate unacceptable bias toward past data at the expense of the rise to come. Indeed, the rise to come should not be ignored by selecting an averaging period that only uses past data. Instead, it makes sense to look at both past data and projections into the future and to also take into account potential acceleration of the rise due to compound impact of feedbacks and further mechanisms, as discussed further below. The image below uses a 20-year averaging period centered around the end of May 2025. If the temperature rise followed a cubic trend based on data going back 1 decade, the rise averaged over the entire period would be 5.79 degrees Celsius, while the rise would cross 5 degrees Celsius in late 2031 and would cross 8 degrees Celsius at the end of 2034. Click on images to enlarge. If an even longer averaging period was used. In the image below, the inset is added to confirm that the temperature rise vs 1903 to 1912 has been 1.5 degrees Celsius or higher for each of the past 24 months. The trend in the image covers a 30-year averaging period, centered around the end of May 2025. The trend confirms indications that the temperature rise would be high and cross 8 degrees Celsius in 2037 and 10 degrees Celsius in 2039. Click on images to enlarge. In other words, the longer the averaging period, the more the trend will be based on, and may be biased toward, data going further back in the past when temperatures were lower and feedbacks were weaker. As temperatures rise over time, however, feedbacks are likely to get stronger. Furthermore, tipping points may get crossed and black swan events may occur. As an example, crossing the cloud's tipping point at 1200 ppm CO2 could, on its own, push temperatures up by an additional 8 degrees Celsius globally, which may occur well before 2028, as discussed further below, and such tipping points should not be ignored. Indeed, much depends on the strength and combined impact of feedbacks and further mechanisms that could accelerate the temperature rise, so the more reason to discuss them in more detail. There are many conditions contributing to even higher temperatures. Emissions and temperatures have recently been rising at a rate that is unprecedented in history. The temperature rise may accelerate further, and there are many conditions, feedbacks, and further mechanisms that point at further acceleration. Earth's energy imbalance has more than doubled in recent decades, and reached 1.8 W/m superscript 2 in 2023, twice the best estimate from the IPCC, after having more than doubled within just 2 decades, as illustrated by the image below, from Moritzen, 2025. Below is a video in which Paul Beckwith discusses the study led by Moritzen. Paul's video has the title, 57 Scientists, at 46 Institutions, co-author 4-page paper ignoring almost all James Hansen's EEI work. James Hansen attributes 1.05 W/m superscript 2 of the albedo loss to the cloud's feedback, 0.15 W/m superscript 2 to the snow/ice feedback, and 0.5 W/m superscript 2 to changes in shipping regulations, aerosol forcing. James Hansen blames the IPCC for failing to warn about the impact of many feedbacks and further mechanisms that are causing albedo loss. Indeed, the IPCC keeps downplaying the dangers in many ways, such as by ignoring a potentially much higher historic temperature rise and rise to come. Paul Beckwith highlights that the 57 authors of the study are merely calling for a robust and reliable capability to observe the energy imbalance, without calling for more effective climate action that includes an overhaul of the IPCC narrative. Concentrations and emissions of greenhouse gases are high and rising. The image below shows recent carbon dioxide, CO2, concentrations at Mauna Loa, Hawaii. The image below shows monthly CO2 at Mauna Loa, Hawaii. Black Swan Event 1. Crossing the clouds tipping point. The image below shows the same monthly data, this time from May 2022 through May 2025, with a trend added that warns about 1,200 parts per million, ppm, getting crossed in 2028. Crossing the clouds tipping point at 1,200 ppm CO2 could, on its own, push temperatures up by 8 degrees Celsius globally, in addition to the temperature rise caused by the extra CO2 to reach the tipping point. Moreover, the cloud's tipping point is actually at 1,200 ppm CO2e, carbon dioxide equivalent, so when taking into account the impact of growth of other gases, strengthening feedbacks, and further mechanisms, this tipping point could be crossed much earlier than in 2028, potentially as early as in 2026. Crossing the clouds tipping point early could be regarded as a black swan event. Black swan events are events that are unforeseen in climate models. Such events can suddenly and unexpectedly increase temperatures. While there have been many warnings about such events, they are typically ignored or minimized in climate models. In fact, many warnings about acceleration of the temperature rise are ignored in climate models. 10 black swan events are identified in this post. Since black swan events are inherently unforeseen in climate models, there is little or no discussion about them, and there may be many more of them on the way than the 10 that are mentioned here. The situation is also dire regarding other conditions, i.e. concentrations and emissions other than CO2 are also higher for further gases and aerosols, also fueled by fires and war. While sea ice is low, the jet stream is distorted, AMOC is slowing down and sunspots are high. On top of this, there are numerous self-amplifying feedbacks that can dramatically accelerate the temperature rise, and mechanisms are in progress that increase temperatures, such as reductions of aerosols that are currently masking the temperature rise. Not only are many of the feedbacks self-amplifying, strengthening feedbacks and changing conditions can also amplify each other, e.g. a freshwater lid can form at the surface of the North Atlantic and a distorted jet stream can combine with hurricanes to cause more ocean heat to get pushed toward the Arctic Ocean underneath this lid, and subsequently speed up sea ice loss and cause eruptions of methane from the seafloor of the Arctic Ocean. Formation of a freshwater lid at the surface of the North Atlantic. There are further tipping points, in addition to the above-mentioned clouds tipping point. Tipping points include loss of Arctic sea ice and loss of the latent heat buffer as Arctic sea ice disappears. Crossing such tipping points can abruptly and strongly increase temperatures and thus trigger crossing of further tipping points. Black Swan Event 2. Early El Niño models do not predict the next El Niño to appear soon, as illustrated by the image below. Instead, NOAA expects La Niña to return in the Northern Hemisphere fall and winter 2025-26. Nevertheless, the next El Niño may emerge earlier, and it may be a strong El Niño, a black swan event, outside model predictions. Over the past few months, there's been a zigzag pattern of rises and falls in sea surface temperatures in Niño 3.4, an area in the Pacific, inset, that is critical to the development of El Niño, as illustrated by the image below. On June 20, 2025, the temperature in Niño 3.4 reached 27.99 degrees Celsius, an anomaly of 0.54 degrees Celsius vs 1982 to 2010. An El Niño event is defined by NOAA as an episode of at least 5 consecutive 3-month running mean sea surface temperature anomalies vs 1971 to 2000 surpassing the threshold of 0.5 degrees Celsius in the Niño 3.4 area, as illustrated by the image below. A new El Niño may act as a catalyst, triggering the joint occurrence of several black swan events, as described further below. Black Swan Event 3. Low sea ice. One feedback of high temperatures and high concentrations of greenhouse gases is loss of sea ice. Polar amplification of the temperature rise is hitting the Arctic hard, and is also causing dramatic loss of Antarctic sea ice. Global sea ice area has been very low over the past few years, as illustrated by the image below, something that wasn't anticipated in climate models. Low global sea ice comes with dramatic loss of albedo, i.e. a lot of sunlight was in previous years reflected back into space and it is now instead getting absorbed by the sea surface. On June 2, 2025, global sea ice area was 17.52 million square kilometers, lowest on record for the day. Arctic sea ice is in a bad shape. The image below, adapted from nsidc.org, shows that on June 21, 2025, Arctic sea ice extent was 10.211 million square kilometers, lowest on record for the day. The image below, adapted from ads.nipar.ac.jp, shows that Arctic sea ice extent reached a low of 9.38 million square kilometers on June 23, 2025, the lowest on record for the day. Low sea ice can also be regarded as a black swan event, the more so since there currently is no El Niño present, but instead ENSO-neutral conditions currently dominate. Importantly, low sea ice does increase ocean heat, as discussed next. Black Swan Event 4. Loss of lower clouds. Loss of lower clouds is discussed before at the clouds tipping point, CTP. Crossing the CTP may not take place immediately, but even so, that's no reason to ignore that there has already been loss of albedo, reflective power, due to loss of lower clouds for decades. The refusal to include this loss in climate models warrants its treatment as a separate black swan event. James Hansen, inferred contributions to reduced Earth albedo. The image below shows a huge drop in the Earth's albedo over the years, and the image on the right, from an earlier post, shows inferred contributions to this drop by Hansen et al. There is compound impact in that sea ice loss comes with albedo loss that causes more heat to be absorbed by oceans, while higher global sea surface temperatures also cause further loss of lower clouds, further reducing albedo and thus accelerating the temperature rise. Polar amplification of the temperature rise narrows the temperature difference between the poles and the equator, which causes distortion of the jet stream that in turn results in more extreme weather events. A 2025 study led by Tsilioutis suggests that this causes the band of clouds over the tropics to contract. Since clouds over the tropics reflect relatively more sunlight, this results in reduced global albedo. The extraordinary albedo loss depicted in the above image may result in further acceleration of the temperature rise and further occurrence of blue ocean events, such as a blue ocean event in the course of 2025, as discussed next. Black Swan Event 5. Blue Ocean Event on June 2, 2025, Arctic sea ice area was second lowest on record for that day, only slightly higher than 2016. Significantly, 2016 was a strong El Niño year. On June 2, 2025, Arctic sea ice area was 0.44 million square kilometers lower than on June 2, 2012. If the sea ice area will be 1.34 million square kilometers less than 2012 on September 12 this year, there will be a blue ocean event. From earlier post. And the video below, with the title Scientists Shocked, again, as ice disappears, Guy McPherson reflects on news that scientists are shocked to see sea ice disappear. Black Swan Event 6. Loss of latent heat buffer volume and thickness are two further measures to assess the health of Arctic sea ice, and they are critical in regard to the latent heat buffer, which decreases as sea ice, permafrost, and glaciers disappear. Latent heat is energy associated with a phase change, such as the energy consumed when ice turns into water. During a phase change, the temperature remains constant. As long as there is ice, additional heat will be absorbed by the process of ice turning into water, so the temperature doesn't rise at the surface. From albedo, latent heat, insolation and more. Arctic sea ice volume, click to enlarge. The amount of energy absorbed by melting ice is as much as it takes to heat an equivalent mass of water from 0 to 80 degrees Celsius. The energy required to melt a volume of ice can raise the temperature of the same volume of rock by as much as 150 degrees C. Warmer water flowing into the Arctic Ocean causes Arctic sea ice to lose thickness and thus volume, diminishing its capacity to act as a buffer that consumes ocean heat entering the Arctic Ocean from the North Atlantic. This means that, as sea ice thickness decreases, a lot of incoming ocean heat can no longer be consumed by melting the sea ice from below, and the heat will therefore contribute to higher temperatures of the water of the Arctic Ocean. Arctic sea ice volume, click to enlarge. Similarly, there is a point beyond which thawing of permafrost on land and melting of glaciers can no longer consume heat, and all further heat will instead warm up the surface. The image on the right shows that Arctic sea ice volume has been at a record daily low for more than a year, reflecting severe loss of the latent heat buffer. Loss of the latent heat buffer constitutes a tipping point. Beyond a certain point, further ocean heat arriving in the Arctic Ocean from the Atlantic Ocean and the Pacific Ocean will no longer be able to be consumed by melting sea ice from below. The combination image below shows Arctic sea ice thickness on April 28, 2025, left, May 13, 2025, center, and June 13, 2025, right. Arctic sea ice thickness. Click on images to enlarge. The image below shows Arctic sea ice thickness on June 15, 2025. Black Swan Event 7. Seafloor methane eruptions. Further incoming heat therefore threatens to instead reach the seafloor of the Arctic Ocean and destabilize methane hydrates contained in sediments at the seafloor, resulting in abrupt eruptions of huge amounts of methane, in turn threatening increased loss of permafrost, resulting in additional emissions, as illustrated by the above image and the image below. The buffer is gone. From earlier post, click to enlarge. Heat danger is especially large in the East Siberian Arctic Shelf, ESAS, which contains huge amounts of methane and which is hit strongly by the temperature rise, as described in earlier posts such as this one. Methane in the atmosphere could be doubled in March 2026 if a trend unfolds as depicted in the image below. A rapid rise is highlighted in the inset and reflected in the trend, which is based on January 2023 to October 2024 methane data, as issued in February 2025. Double the methane in March 2026. Image from earlier post, click on images to enlarge. Rise like the one depicted in the trend could eventuate as rising ocean heat destabilizes methane hydrates contained in sediments at the seafloor of the Arctic Ocean. The temperature rise in the Arctic would accelerate since the methane would initially have a huge impact over the Arctic and cause depletion of hydroxyl, of which there is very little in the atmosphere over the Arctic in the first place. Such a rise in methane would also dramatically increase concentrations of ozone in the troposphere and concentrations of water vapor in the stratosphere. The image below with high monthly methane recorded at Utqiagvik, Barrow, Alaska, should act as a warning. Discussed earlier on Facebook. Here, click on images to enlarge. High monthly methane resulted from very high recent hourly methane levels, as illustrated by the image below. Discussed earlier on Facebook. Here, click on images to enlarge. Black Swan Event 8. Water vapor. The temperature rise itself comes with many self-reinforcing feedbacks such as further loss of snow and ice and changes in clouds, wind patterns, and ocean currents, and this can cause rapid additional warming and thus extra water vapor, which also constitutes a self-reinforcing feedback, since water vapor is a potent greenhouse gas. The IPCC has failed to warn about the size of the temperature rise. Higher temperatures imply stronger feedbacks, such as stronger evaporation resulting in both a lot more water vapor and a lot more heat getting transferred from the surface to the atmosphere. Much of this will return to the surface with precipitation such as rain and snow, but 7% more water vapor will end up in the atmosphere for every degree Celsius rise in temperature. Moreover, water vapor is a potent greenhouse gas that will increase temperatures, and it is a self-amplifying feedback that can strongly contribute to further acceleration of the temperature rise. From April 2024 post, click on images to enlarge. As illustrated by the above image, the temperature rise from pre-industrial to February 2024 could be as large as 2.75 degrees Celsius, which corresponds with almost 1/5 more water vapor in the atmosphere. Water that previously remained present in the ground, is increasingly moving up into the atmosphere, since a warming atmosphere holds more water vapor and thus sucks up increasingly more water. The water vapor feedback results in more moisture getting sucked up into the air as temperatures rise, a process that is further accelerated by stronger wind as temperatures rise. More transpiration from vegetation and more evaporation from rivers, lakes, and the soil contributes to stronger drought and makes vegetation more vulnerable to pests and diseases, and also makes both vegetation and the soil more prone to get burned. After fires, the soil turns black, reflecting less sunlight back into space, and is more vulnerable to erosion and to further droughts and fires, having lost the vegetation that previously held the soil together. Trees keep the soil together with their roots and also keep the soil cool. Because of the lower temperatures, the soil will also retain more moisture. Trees cool the surface by shading it, by transpiration, and by releasing volatile organic compounds into the air that contribute to the formation of clouds that reflect more sunlight back into space and that cause more rainfall. If rainwater can run deep down into the soil along the roots of trees, it helps replenish the groundwater. The land evaporation tipping point can get crossed locally when water is no longer available locally for further evapotranspiration, i.e. from all processes by which water moves from the land surface to the atmosphere via evaporation and transpiration, including transpiration from vegetation, evaporation from the soil surface, from the capillary fringe of the groundwater table, and from water bodies on land. Once this tipping point gets crossed, the land and atmosphere will heat up strongly. Additionally, more water vapor in the atmosphere accelerates the temperature rise, since water vapor is a potent greenhouse gas, and this also contributes to speeding up the temperature rise of the atmosphere, discussed on Facebook. Here, and here. Black Swan Event 9. Abrupt collapse of the West Antarctic ice sheet. A recent study warns that collapse of the West Antarctic ice sheet, WAIS, could contribute over 4 m sea level rise with little, 0.25 degrees Celsius, or even no ocean warming above present, even without additional carbon emissions. The study concludes that we are likely already at, or almost at, an overshoot scenario, and adds that, once on the lower branch, WAIS recovery by tipping back to the upper branch occurs only once the ocean temperature cools between 1.25 and 1.5 degrees C below present. In the video below, Paul Beckwith discusses the study. The very low Antarctic sea ice over the past few years was not anticipated by models, neither was the steep rise in sea surface temperatures. Continued loss of Antarctic sea ice could dramatically increase sea surface temperatures where the sea ice disappears. A further rise of global sea surface temperatures could make things worse. The joint impact could cause abrupt collapse of the West Antarctic ice sheet. Black Swan Event 10. More extreme weather events. Emissions are rising due to continued consumption of meat and continued burning of fossil fuel, forests, wood, and other biofuel. Furthermore, emissions can suddenly increase strongly and rapidly due to fires and lightning strikes, and due to heavy decomposition of biomass as a result of floods, droughts, and heat waves. More extreme weather events can also make vegetation much more vulnerable to pests, diseases, and fire hazards. Peatlands, tar sands, boreal forests, rainforests, and soil can all start to burn abruptly as temperatures keep rising. In the Arctic, where temperatures are rising rapidly, thawing permafrost can release huge amounts of emissions, including carbon dioxide, methane, and nitrous oxide. Soil erosion after fires can cause irreversible loss of topsoil that even heavy rain cannot restore, as there is no vegetation left to hold the soil together, and flash flooding may cause even more erosion. The above image shows annual number of fires and area burned in Canada and is adapted from the Canadian National Fire Database, which adds that while lightning causes about 50% of all fires, it accounts for about 85% of the annual area burned. A 2022 study finds that increases in lightning ignition efficiency, together with a projected doubling of lightning strikes, result in a 39%, 65% increase in lightning-caused fire occurrence per 1 degree Celsius warming. The combination of higher temperatures, stronger wind, more vulnerable forests, and more lightning is causing more fires and more emissions of carbon dioxide, black carbon, brown carbon, methane, carbon monoxide, and tropospheric ozone. At 3 to 8 miles height, during the summer months, lightning activity increases NOx by as much as 90% and tropospheric ozone by more than 30%. Tropospheric ozone has a direct warming impact as a greenhouse gas, while carbon monoxide can indirectly cause warming by extending the lifetime of methane. The worst wildfires can send smoke high enough to affect the ozone layer in the stratosphere. Damage to the ozone layer and climate change are forming a dangerous feedback loop. Black Swan Event 11. War, chaos, and panic. From the extinction page, the image on the right illustrates how such mechanisms could be amplified by a final black swan event, i.e. the threat of war and the associated chaos and panic. As more people start to realize how dire the situation is, and as they seek to occupy the last few habitable areas left, more people may stop showing up for work, resulting in a rapid loss of the aerosol masking effect, as industries that now co-emit cooling aerosols, such as sulfates, come to a grinding halt. See reductions in cooling aerosols. As it becomes harder to obtain food and fuel for cooking and heating, and as the grid shuts down due to conflicts and people no longer showing up for work, many people may start collecting and burning more wood, decimating the forests that are left and resulting in more emissions that further speed up the temperature rise. As temperatures rise, huge fires could also break out not only in forests, peatlands, and grassland, but also in urban areas, including backyards, landfills, and buildings, in particular warehouses containing flammable materials, chemicals, and fluorinated gases, further contributing to more emissions that speed up the temperature rise. As the likeliness of further accelerating warming, the severity of its impact, and the ubiquity and the imminence with which it will strike all become more clear and manifest, the more sobering it is to realize that a mere 3 degrees Celsius rise may suffice to cause human extinction. Compound effect of several ignored black swan events. Black swan events may be unexpected and they are typically excluded from models that seek to downplay the dangers, but that doesn't mean that black swan events should be ignored. Using nonlinear trends may show surprising developments, but at times they can turn out, in hindsight, to be surprisingly accurate, as developments may unfold faster than previously expected, as illustrated by the combination image below. Screenshot from earlier post, click to enlarge. It may take some time for a black swan event to occur, that's the inherent nature of a black swan event, but that's no reason to exclude them from climate models. Moreover, several black swan events can combine with catastrophic results, so to keep ignoring them amounts not only to scientific deceit of unimaginable proportions, as the very existence of life on Earth is at stake. The image below, adapted from NOAA National Weather Service, shows high wet bulb globe temperatures forecast for June 24, 2025, 1800 hours UTC, as high as 92 degrees Fahrenheit or 33 degrees Celsius at a location 20 miles SSE of Williamston, North Carolina, US. Temperature, 100 degrees Fahrenheit or 38 degree Cap Arent temperature, 110 degrees Fahrenheit or 43 degrees C. Dew point, 73 degrees Fahrenheit or 23 degrees C. Relative humidity, 44% high wet bulb globe temperatures at high altitudes in June 2025. The combination image below shows that feels like temperatures as high as 43.7 degrees C or 110.06 degree FR forecast. For June 24, 2025, 1800 hours UTC, at the green circle, image left. The jet stream is forecast to move as fast as at 177 miles per hour or 285 kilometers per hour over North America, circle image right, to split over the North Atlantic with one of the branches moving back to the US and down over Mexico. Extreme weather events may look like one-off events that may do huge damage, but that have an impact that is temporary. A local emergency may therefore be declared that is temporary. In the case of black swan events, their impact can by contrast increase over time and accelerate. The probability of getting hit by an extreme weather event may seem low, but as temperatures rise, the probability increases. An increase in the probability that more extreme weather events will occur can thus be regarded as a black swan event, which is largely ignored by the IPCC and others who seek to downplay the temperature rise. Note that probability is only one out of 3 dimensions to be used to assess the danger. The longer climate action is delayed, the more the danger will increase, especially when tipping points get crossed, which makes that imminence itself constitutes a second separate dimension. And while black swan events may be hard to predict, that is no reason to entirely exclude them from an assessment of the danger. A third dimension is the severity of the compound impact of all mechanisms that are accelerating the temperature rise across the globe. Extreme weather events and black swan events can strike with increasing strength, frequency, and duration. There is also an increase in ubiquity, i.e. events can cover larger areas and multiple events can increasingly hit multiple areas at the same time. Image from earlier post. Indeed, the very continuation of life on Earth is at stake, and the sheer potential that all life on Earth may be condemned to disappear due to a refusal by some people to do the right thing, that shouldn't cause people to be stunned, but it should prompt the whole world into rapid and dramatic climate action. Climate emergency declaration. The situation is dire and the precautionary principle calls for rapid, comprehensive, and effective action to reduce the damage and to improve the situation, as described in this 2022 post, where needed in combination with the climate emergency declaration, as discussed at this group. Links: NASA, GIS surface temperature analysis /data.gis.nasa.gov/gistemp